Good morning, good afternoon, and good evening to all our attendees joining us today for this latest Iot Central webinar. This is David Oro, your host. I am the editorial director with Iot Central. I'd like to start off by thanking Vertica for sponsoring today's event. Vertica is a wonderful supporter of the Iot Central community, and we are honored to have them as sponsors. This webinar is entitled Scalable IoT in Database Computing. Before we begin, I'd like to briefly review the format of today's webinar. The event will be 1 hour long. We will have two panelists that I'll introduce in just a minute. There will be a 10 to 15 minute Q&A following the presentation. And this event is being recorded and will be available on iotcentral.io later this afternoon following the live event. I'd also like to encourage our attendees to provide questions throughout the presentation. We will be reviewing and presenting them on your behalf during the Q&A portion of the event. I'm very pleased to introduce today's speakers, Dina Shaw-Handy and Benjamin Smith. Dina has contributed to a variety of startups in the Toronto ecosystem by creating and leading data science teams. He has been Director of Data Science at Ecobee, a pioneer of IoT and smart home technology. Together with an interdisciplinary team, they design and implement machine intelligence into the products. Dina's background is in scientific computing with a PhD from the University of British Columbia. His publications in prestigious scientific journals have been selected as featured articles and received the James Clerk Maxwell Young Writers' Prize. Ben Smith is a senior manager on the Vertica product marketing team, where he supports go-to-market planning, content development, marketing campaigns, and competitive research, and more. Ben is a Vertica product evangelist, has a background in IoT, and a passion for clean energy and smart building analytics. Thank you for being with us today. We look forward to the presentation. The Internet of Things data is exploding, driven in part by the adoption of connected home technologies such as smart thermostats. While the adoption of connected home technologies is increasing at a dramatic rate, creating value from the growing volume of sensor generated by smart devices requires a new approach to advanced analytics at an increasing scale. In today's Iot Central webinar, we will learn from Ecobee, a maker of Wi-Fi-enabled smart thermostats, how they leverage Vertica's advanced analytics to process massive raw data clusters at scale to build thermal models so customers can intelligently manage heating and cooling systems and contribute to a sustainable future. During this presentation, we will explore how Vertica in database machine learning uses massive parallel processing and a familiar SQL interface to accelerate time to value on predictive analytics projects. Ecobee's Vertica implementations and broader analytics stack allows them to answer analytics and data science question faster, and also how Ecobee is using smart thermostats and data analytics to unlock new innovations around demand response management, time of use optimization, and energy storage. Dina and Ben, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Great. Thank you, David, and thank you for the introduction, and thank you to the audience for joining today's webcast. My name is Ben Smith, and I'm a member of the Vertica product marketing team. I'm excited to kick off today's webcast with a brief introduction to Vertica and a review of our IoT and machine learning capabilities before I hand it over to Sina, who's going to talk about his work at Ecobee. So for those on the line who are not familiar with Vertica, Vertica is an advanced analytics platform built from the very first line of code to handle big data. The Vertica unified platform provides blazing fast speed, exabyte scale, and an ecosystem-friendly architecture, all at a much lower cost than traditional data warehouse solutions. It's available in the cloud, on-premise. It can also run natively on Hadoop. So how does Vertica provide blazing fast analytics? The Vertica platform is consciously designed with speed, scalability, simplicity, and openness at its core, and is architected to handle analytical workloads via distributed compressed columnar architecture. It leverages a standard SQL 99 compliant interface, advanced machine learning functions, integration with all the leading ETL, BI, and visualization tools your company might be using. And advanced compression provides up to 90% space reduction, and Vertica executes queries using an MPP no-leader node architecture. What does this all mean? It means Vertica customers can take queries that were previously run overnight and run them in under 10 minutes, or a query that took an hour on legacy systems can now run in minutes or even seconds, all with high concurrency and the ability to scale up and down depending on your company's data volumes and needs. And as I mentioned before, Vertica meets you where you operate. The same unified Vertica platform can be deployed on-premise, in the cloud, including on AWS, Azure, and with our latest 9.0 release on the Google Cloud Platform as well. Vertica can also run natively on Hadoop if you want to bring advanced analytics, SQL analytics, and enterprise-grade analytics to your Hadoop data lake. So before handing over the reins to Sina, I did want to give everyone on the call a quick overview of Vertica's IoT and machine learning capabilities. So although designed for analytics at scale across any number of use cases, Vertica in many ways is purpose-built for IoT data. Vertica integrates with Apache Kafka for high-performance messaging, enabling distributed data pipelines for high throughput and low latency data ingest into Vertica. We have powerful time series functions for arranging and analyzing sensor and machine-generated data on the same timescale. Vertica Flex Tables are a cost-effective way to store and explore semi-structured data without the creation and maintenance of time-consuming schemas. You can easily load, explore, and analyze semi-structured data from sensors, log files, or other machine data in Vertica. We have a range of geospatial functions which allow users to manipulate complex 2- and 3-dimensional spatial objects following the OGC standards. Geospatial functions, for anyone who's familiar with IoT analytics, are really crucial for analyzing IoT devices and sensors that are geographically dispersed. And since many companies are storing vast volumes of IoT data in data lakes, integration with open source solutions like Apache Hadoop is critical as well. And perhaps the most important feature of Vertica that supports new, innovative IoT and predictive analytics use cases are our in-database machine learning functions, which allow customers to bring the power of machine learning directly to the data. So predictive models can be trained, scored, and deployed at greater and greater scale. And I'll get into that in more detail now. So by building advanced machine learning functions directly into the core of Vertica, we are transforming the way data scientists and analysts across industries interact with data, removing barriers and accelerating time to value on predictive analytics projects. The same core analytics engine I mentioned before that allows customers to run SQL functions at extreme speed and scale in an MPP environment can now be used for machine learning as well. This eliminates much of the current data duplication that exists today, where data must be moved from databases to statistical analysis tools and then back. There's no more need for downsampling data because the machine learning functions can run directly in the database, just scale up or down depending on your performance need or data volumes. You can now have a single system for both SQL analytics and machine learning and predictive analytics. To unlock machine learning for the growing speed and scale of business needs, we've built out functionality that supports the entire machine learning process. Predictive analytics are run in massively parallel processing architecture, where Vertica customers regularly see a 10 to 50 times or more performance improvement versus legacy database systems. And all of this can be run using a familiar SQL interface, so you can manage and deploy machine learning models using very simple SQL calls. And for those currently writing in R, Python, Java, or C++, Vertica customers can write their own user-defined functions in those languages and then execute those functions in parallel across Vertica clusters. And I mentioned the entire machine learning process before. I think this is a pretty common theme within Vertica's development in the machine learning area. To support customers with the entire machine learning process, Vertica has functions for data preparation, modeling, evaluation, and more. When most people think about machine learning, they tend to think about the most common algorithms: linear regression, logistic regression, naive Bayes, and so forth. Vertica has all these functions built in, but we recognize that data scientists spend a significant amount of their time prepping the data for analysis. So functions for outlier detection, missing value imputation, normalization, and others will reduce the time it takes to prepare data so customers can spend more of their time creating and deploying predictive analytics models, and hopefully reduce the time to value on data science projects. And of course, all the typical model evaluation tools are available for customers as well. To wrap up, I just want to emphasize that in addition to IoT use cases with customers like Anritsu, Optimal Plus, Nimble Storage, and others, Vertica is trusted by some of the world's leading data-driven organizations in a range of industries, including financial services, healthcare, advertising, telecommunications, gaming, and virtually any business that wants to transform massive volumes of data into meaningful insights. If you want to learn more, you can check out our machine learning capabilities at vertica.com/machine learning. We also recently published a great paper on IoT analytics with Harvard Research, which you can access through the link I provide on this slide. And of course, if you have any questions, you can feel free to reach out to me directly after the webcast, and I'll try to have those answers provided to you as quickly as I can. So thank you for your time, and now I'd like to hand it over to Sina, who will talk about the amazing work Ecobee is doing with smart thermostats and IoT data. Sina, I'm going to hand it over to you.
Thank you, Benjamin, and hello, everyone. So my name is Sina Shahande, and I'm Director of Data Science at Ecobee. So the talk that I have will give you an overview of what we do at Ecobee and how we deal with the IoT data, how do we perform some of the computations that is required for analytics in our system, and then how we use Vertica in specific along the way process. So it's background of why the thermostats matter, why the smart thermostats matter, why Ecobee matters. You have to look at the energy consumption across, for example, US. You would see here that residential energy consumption is about 22% of entire energy used across the human activity. And out of the energy in the house, about 45 to 50% is around basically heating and cooling, air conditioning. Uses about 50% of energy in the house. Now, the question comes up is that how can we basically save energy from this huge amount of energy being used? How can we kind of curb a little bit of the energy? If somebody can save 10 or 20% of that energy, you would be much higher, great impact in the entire energy consumption of the entire house. So you would see the Internet of Things explosion can help this process. So one of our ideas that if you have a smart thermostat, that smart thermostat can control energy consumption in your house, then you would be able to, with that, deliver certain value. Now, what is that, to put in context, this smart home, I think everybody has a very good understanding of what that is. The particular point of view of IoT, where it applies to smart home, is where the human involved. So, in comparison with other machine data or industrial applications or sensor networks, such and such, when you have the human element and IoT, that's where you go into the kind of smart home space, connected home space, where the idea is that appliances would be able to interact with the environment and understand from what's happening in the environment, what's happening from inside the house, and react to it. So think about it as our idea with the smart thermostat or with any new products that we have in mind is can I make an agent, a smart agent in the house, like almost a robotic being that understands the environment inside the house and understands the environment outside, for example, weather conditions, and able to respond to that environmental behavior and adapt to it. So almost like think about a self-driving home. self-adapting home, understands the environment and reacting in a smart way. The product that we had, since we're one of the pioneers of the smart thermostat, one of the early companies that kind of started the idea. Basically, we had a few products along the way since 2007, and there are current product that's in the market is Ecobee 4, where it has Alexa built in and equipped with the room sensors, so you can put the network of these room sensors across the 8 different places, and then all that sensors sends data to the main thermostat, and data is the temperature, the humidity, and then the device makes a decision. In a way, it's the only product out there that has this kind of room sensor network. And that room sensors network would allow quite a bit of more detailed information about the house and how does it function. And you can control the temperature across the
Hi, Sina. This is David here. Just wanted to make sure we're getting a number from our audience to speak up a little bit louder, please, to come across more clearly.
Sure. I have my sound up here, and I'm going to shout a bit. Okay. So the effect of the smart thermostat is actually quite large. So we have around, we estimated, we calculated this, that we have around up to 23-25% savings a normal house can be delivered by using a smart thermostat. And the way to achieve that, basically shaving off one home that has a thermostat can shave off the entire energy consumption of 10 houses. Usually they control the system. The system that drives savings is through adjustment the heat when people are not home. So when you have occupancy data, when you have temperature data, you would basically be able to say, if somebody's home, if they're not home, you automatically reduce the setbacks, allowing people to use more smartly. They adjust their schedule and adjust their controls. Will allow them to save energy, to reduce the heat when there's no need for it, reduce cooling when there's no need for it, and then they'll drive those savings. Now, besides the kind of basic functionality of thermostat as this kind of schedule and understanding of the occupancy, augmented panels, there are very interesting applications one can do with the data. And that's the idea of the energy services. So basically deriving, so now ability, think about it this way. So now you have the utility driving energy to the house. And you have the house as a basically almost like, think about it as a box. It can consumes energy, but also stores energy. And stores that heat, stores cool inside the house. And then you have a time in which it diffuses out to the environment. Now, depending on time of basically the electricity cost, it might be time dependent, or a utility might have a different peak time where many people come home, and then there's a high demand at a particular area. There's ideas with the renewables where they're generating lots of energy in a particular period of time, and then somebody needs to store this energy somewhere, and then use it at a time where people don't less want to use it. Now, home is becoming kind of an idea where the home can act with its thermal capacity as an energy storage, but not just energy consumption, which I'm going to go through it in detail. So you can go beyond using these IoT devices, using this kind of ability to control fleet of homes across a particular region. Then you can kind of deliver services, deliver solutions where it would never been possible. So where all the data is and how does it fit? So we have a data, our basically entire data infrastructure is something like that you would see here. So data is generated from a variety of sources, mainly this production environment on the left-hand side. You would see there are various points of data generation. So you have thermostats and room sensors, each of them every 5 minutes send temperature data, humidity data, and also occupancy, whether that room was occupied or not, using the infrared sensors. And those information is being relayed to the thermostat, and the thermostat sends them to the server. And there's also analytics data coming from the fact that if you change something on your phone, change something settings on your thermostat, on the web, these data also get collected, basically all the set points when people interact with the device. And also there would be there's log data, information about alerts, what's happening from the way the HVAC system works. All these gets logged into the process. And then there's also other data across the company as well, like how basically overall operational data that we get from the company basically generates around sales and marketing and what happens from the users and who opens that email, such and such. All this data comes in, gets ETL, and it comes to this analytic layer, which is basically our data lake. And in this area, we have, of course, this data. We use AWS, and we have also in-premise data center that we use both as a sort of hybrid solution. And we have Amazon S3 to store some of the data, and then we have a variety of databases that we use from RDS. We use Redshift, we use Elasticsearch, and we use Vertica. And on top of these databases, we have these different analytics tools, visualization tools, whether it's a data science group uses Python or R, if we have Tableau, or different Kibana is for accessing the Elasticsearch logs, and Redash for kind of allowing people to do custom queries. So there are different ways you can kind of expose this data. Now, across this process, you would see that you would bring data, and then you need some sort of tools to manage it. And this is the middle layer is the critical part. So that's where the data lake is. And that needs to be some sort of responsive and allow the access to data in a more efficient way. So the way we use Vertica in particular is that we had this process where we started with actually we had our data is in MySQL databases traditionally, and we transitioned that data. That data is good for production environment, but not good for analytics purposes. So we can't query the history of this person in the past year, what happened to their temperature, what was the last winter, how did they use it. So for those kinds of queries, we need to have a database. So we used initially Redshift, and we realized that wasn't a good solution for us, and then we could have switched to Vertica. And for the switching, we used a process to basically make that up and running. I'm sure everybody's familiar with that. So basically, finding the schema that we want to do, we changed our data in a way. I'm going to take into account. So the Vertica, the columnar database is very different than the transactional databases and the log transactions that we have. The transferring data to fit the Vertica paradigm, the columnar database paradigm, is an important component. And then we were able to kind of do the rest of the process by loading data, deploying, testing, and following the process. Now, here's the part that I want to emphasize here, where when you have a data log coming from a variety of services, so each of these sensors randomly shooting out things, and so data comes in, the capture process is very transactional. So data comes in at different times, with a different date, the ID, the time, and then there's value for that, so it comes in. Now, this particular setup is very good for capturing or sorting the data that comes in, but for analytics purpose, it's not good as much because the analytical databases, they are very columnar in nature, because sometimes you're looking for a particular sensor, particular person, a particular date range, and you're looking for that particular sensor attribute. Whereas in the transactional system, you would put every sensor. Say sensor 1 said X, sensor 2 said Y, and so on and so forth. You transition the system to a way that each column now represents a sensor. Now, what happens is that before you had a very nice and tiny column table where you say sensor 1 said this, sensor 2 said that. Now you kind of turn it into sensor 1 has its own column, right? So basically you repeat, and then there's moments where there's zeros coming in the middle. So you basically kind of expand the table very large and many columns. Now, Of course, this system, we think it's going to take much more space, but the point is those values for each particular timestamp and particular value of the sensor might be null or empty, but then a database like Vertica would take that null space as null, so it wouldn't actually really take space in a smart way. It's as a sparse data structure, so it would not treat it as extra, basically data point, extra volume. And this allows you to basically search a very particular column very fast, which adds the speed. So lots of the speed came for us from this particular procedure where we basically flatten our tables more columnar shape. You would see it similarly. So you have before 12 column table, now we turn it to 102 column table. Now these very, very columnar systems are not very compatible with the old like MySQL databases paradigm, the more analytical database would handle. Now, when the data is loaded, now we could do more fast queries. So now I'm going to take a look at show you an example of the data that you would see here. For example, this is a particular home across the x-axis time. You would see as time goes by if you do a query. Sometimes the type of query we need to do is to say, I'm looking for this person, this room, what was the temperature history at this room of this house. Basically, you want to basically train a thermal model to see how the house responds to the environment. So, for example, the wind. How wind affects the cooling in that room. You need to find out history of times where the wind was blowing and history of times where the temperature was there to be able to understand how that room is affected by wind, for example. Now, in this case, you would see the temperature comes in, there's kind of small fluctuation, and the red line here is the set points that use the set points. You would see, they choose different set points, maybe the time home or the away, and temperature kind of fluctuates across. At the same time, you have the data from outside. So this blue line here is the outdoor temperature. So here's the winter time where temperature is cold here, and then the house is heated, and you would see if the time where somebody's not home or they turn off the HVAC, the temperature kind of starts declining, and then when you come back again, when the set points change. You would see, for example, one of the smart features here in the thermostat, the smart thermostats, where as somebody is not home, set points has changed, the temperature declines. But then, without them coming, the thermostat knows that they're arriving at a particular time in the future, and then the temperature goes up in the middle of the set points. So when they are home, the temperature is right at the time that is. That's how thermostat, if we can save energy, because you don't need to you can go very deep setbacks when you're not home, and you know when you're home, it knows when your schedule when you're coming through geofencing or through the schedule, so it adjusts itself. So you never know that your house was cold while you were not there. So that's how the thing is. Anyway, so let me show you some things about the database. So this is where we actually found our performances. Now the chart is basically different data that you pull in, similar to the chart that I just showed you, for different lengths of days. And you would see, for example, for one day, the blue line is the production environment that we have in MySQL. The yellow is the redshift without flattening, and the Vertica is the performance of the Vertica number of seconds that comes out with the flattening. And you would see the Vertica for one day it looks like a production, not so good with the redshift. But then when we go to a large period, the production environment increases the time, but Vertica still remains small. And that shows that Vertica is doing a distributed computing. So it basically distributes the load across multiple nodes, and that's how it can scale in a very slower pace. Now, what you see here is the data that comes out from the database and then gets processed. Now, in many cases, you have situations where you have data coming out of the database, and now you need to do computation on the database, for example, outside, for example, Python or processes. That would be much faster if we can save the data somewhere, if we don't pull the data out of the database, but send the computational algorithm inside the database, and that's where the in-compute database in database computing comes in. So you want to push the data as close as possible, and this is possible with Vertica with the built-in function that it has. But also, if someone has a Python script, they can do it. To the best of my knowledge at this point, Vertica is not able to do vector-based computation. It would be scalar-based computation of the data. But this is something that and it's important where you can actually do vector operations. By vector operations, I mean where you can take the entire column and do manipulation on it. So that way, you can kind of build a custom script to the Vertica and then done it. At this kind of stage, the Python and R system will work on scalar functions, where you need to, for example, find a particular function in which only you code it. And this function can be sent to the database, can run on a Python script that runs with the data. I mean, it's out a particular operation. So you can kind of say, select, rather than select, do this function on my data, and that function is a Python function. Now, let me take you to some sort of interesting applications here where we look at demand response situations where, I'm talking about where you have this. If you talk about one home, savings for one home. Now the question becomes, if I have many homes in a neighborhood or in a city, 10,000 homes, can I do something with that 10,000 homes on the utility scale using this IoT devices that were not even possible in the past? Now, here's an example of what you see here of demand on the grid. And this demand on the grid is, so it's a 24-hour period, and you would see here, kind of the blue curve is a typical demand. Now, it goes up the yellow line if you do not have any demand response. So when people come home, for example, everybody come home, there's still systems running on the companies, but also people going out at home. So you have two places to warm up, both companies and more offices and residential. So there's a peak happening in the energy consumption. And this peaks a challenge for the grid because the grid capacity is limited. Now, if you push the peak, then somehow it reaches the edge of the capacity of the system. And you sometimes have to have all this electricity systems, all the electricity grid, just to service this peak, whereas most of the time it's much below it. So the question is, can we reduce that peak? If the thermostats knew that when the peak comes in, so we can kind of, just right when people come in, we can respond to this. And so there's people coming in with the idea of demand response. And the idea is that kind of your house becomes part of your utility system, together with a device like a smart thermostat. So let's look at this graph here. I'm going to come here, and it's going to show you situations where you would see, so here is an example of a dashboard built in Tableau on top of Vertica data. So you would see here, the orange line here is the time, the x-axis, and orange line here is on the second graph from up top. You would see this baseline of energy consumption. So this would be a baseline of energy used in that particular environment. So you would see this is like almost like a tip of a peak in the utility system. Now, this is the data energy consumption only from the h-axis. So the peak might be a bit different. The peak of which might be everything, right? Not just h-axis. Now, the blue line here is something where we ran a program called demand response. So basically, we call this, say, 1,500 people in this program and in this particular test. And that 1,500 people, we just told them to turn off their HVAC system right at that time. That the peak demand, we want to reduce the peak demand. So from a utility, comes a signal, we say, we need to shed X amount of load. And we say, okay, we're going to shed it up. So we basically turn off we're going to reduce the set points of people by 4 degrees Fahrenheit or 2 degrees, depending on their preference. By doing that, the HVAC system turns off, and you would see that suddenly the load decreases. So that's kind of the fleet of the 1,500 thermostats respond to the peak in the load. And then when the peak diminishes, the utility comes and say, okay, I'm okay now. The system is not under distress anymore. So then we turn off the HVAC system. And you would see when they turn it off, then the HVAC system starts working, and then there's a little peak above the baseline. so the utility knows that this is okay. So this is one of the applications where you need to kind of have the system where you kind of pull the data quickly from the database. You show you analyze what's your level of the peak consumption, what's your energy consumption across this fleet, and then you respond to it accordingly to what needs to be done. Another application is the time of use, where I'm not sure how many people are in that particular program, where electricity is not just constant rate, constant price. The cost of electricity changes by time. So you would see here, for example, the Ontario time of use. So you would see they have it in California. I think would be mandatory in 2019, and other regions as well. They have this kind of time of use pricing, where electricity is more expensive at the peak time and less expensive during the daytime, and then very, very cheap at night, when everybody's sleeping. If that's the situation, then what would you do if a particular time electricity becomes very expensive? The question becomes, can we not use electricity at the time it's expensive, use it when it's cheaper? Almost like you buy it cheap, you sell it expensive. You get a time where it's cheap, you use it, and store the temperature, store the cold or store the heat inside the house. And then when there's a peak electricity cost, then you kind of basically coast over it. And yes, that's possible with the smart thermostat. Now, what has to be done is this curve. So you would see here, again, you would see this green line is the time 24-hour period. The green line is the baseline energy consumption from an HVAC system. And the blue curve is the HVAC system with the smart feature, smart time of use response on. You would know that at this particular time, around 3 p.m., for example, if the electricity comes at a time where you see this peak, where it gets yellow, for example, electricity becomes expensive. So what our smart thermostat does is that it would increase the energy consumption prior to that, turn on the HVAC system, increase the temperature, like reduce, for example, in summer, reduce the temperature, pre-cool your house, and then by the time the peak arrives, it basically turns off the HVAC. So now your house is a bit colder at the time you start. Now, because it's colder, as a human, you can tolerate quite a bit of range of temperature. So that basic temperature comes up, and then it can turn off the HVAC system and coast over it. You would see this better maybe here. So this is a temperature, y-axis is temperature, and the below curves are runtime. You would see this red line coming down, temperature pre-cooled, and then you coast over it, and you can shave off some of the consumptions during the beginning at the peak. At the beginning. Now, if your house is very thermally isolated, you can coast over a longer period because your house can maintain that cool. And if the house is not good, it's not efficient, it kind of lose the heat quickly. Now, behind the scene here, there is a temperature model. So we collect historical data from the thermostat, and we run a temperature model to understand what is the capacity of the home and how long should this cooling occur in order to bring the temperature down in a suitable amount. So there's lots of machine learning happening in the background where data comes in, there's a system Vertica. You run the ML model, you understand the temperature profile, you can predict temperature for the house at a given time. And that you then feed it to this optimization algorithm. The optimization algorithm says, okay, I model the house, I predict that if you turn on your HVAC at this time, you bring the temperature down, and then by the time the temperature slowly comes up, you would be saving a certain amount. And the saving optimization needs to be done using the algorithm that runs on the data. It's a very data-intensive problem. So I hope this gives you a good overview of the entire system and some of the applications that we do. Now, at this point, I think I would open up the floor to questions. Just want to tell you something about the general idea with this smart thermostat and the IoT at home, where your home, from the energy consumption, can do quite a bit of new things that it wasn't able to without this smart thermostat, like or with a simple programmable thermostat. It can be part of the grid, an active part of the utility grid. It can store energy. Maybe at the time where I just showed you the curve where energy gets stored, and you can store the energy when energy consumption is high, energy production is high. So it can act as a storage facility for renewables, for example. It can basically stores energy when the energy is high, or it can shift it to something like your electric car. So basically, together with the electric car and the smart home, you can have this kind of ability to basically play with the source of energy. When electricity generation happens on the solar rooftops, you basically save it into battery in your car, or you can decide to save it into your house. Depending on which one makes more sense at that time, you can make a decision whether which way is the better, which one has a better capacity and respond to it. So that's kind of a future where we see that all this capability of energy storage, you use your house in a very smart way that helps the grid, helps the environment, and be integrated part of multiple energy. Well, that concludes my talk, and thank you very much for your attention.
Sina and Ben, thank you for the presentation. We'll get started with today's Q&A session, and I want to thank the audience for their participation. We have great questions that have come in during the presentation, and we'll do our best to get through all of them in the time remaining. During this Q&A session, I'll leave up this screen with contact information for Sina and Ben if you'd like to contact them following today's webinar. So let's get started. And a reminder to the audience, feel free to use the Q&A portion of the chat box to send additional questions through as we answer these. I think there's just a quick clarification here from a participant. So our scripts are able to run on the Vertica database?
Yeah, I can answer that question, and Sina, if you want to add on, feel free to. But yes, you can write user-defined functions in Vertica that call R scripts. There's an R language pack available for Vertica that you can download and install on each of the nodes in your clusters, which supports scalar and transform functions for R. And I can send more information to the person who asked the question on this after the webcast as well.
Sina, did you want to add to that?
No, that's clear.
Okay, great. All right, so I think this one is actually for you, Sina. It's from the same participant. How do you estimate 25% energy savings per home?
Yes. So first of all, the number is quite varied depending on how you baseline it. So now the way we studied this problem is that we need to question the first baseline that energy consumption. So we set up a methodology where we say, if I keep the temperature at home, so if you get a dumb thermostat and put it at 72 degrees, for example, in your home, that 72 degrees require, to maintain the temperature of the house, and the 72 degrees require a certain runtime. And you basically calculate that by looking at the temperature difference between a house internally and outside, and you do a linear regression between the temperature difference between inside and outside and the actual number of runtime that house had that day. So every day, imagine today your house difference, your house outside was 10 degrees colder than inside, and your HVAC system ran 1 hour to warm up your house to that temperature, desired temperature 72. Tomorrow it's 20 degrees colder, and HVAC system runs 2 hours rather than 1 hour. Now you get a slope of the line relating these two. Now you can do the simulation. You go over every single day across your home, across the year, and then you determine what would have happened at runtime using this curve, this basically the line, and then say what would have happened if the temperature of the house would have kept at 72 and the temperature outside would have changed, depending on the weather conditions. And you get a certain number, certain value for estimated runtime if they keep the temperature of the house at 72. And then you have the actual runtime that comes out of the database where you get it, like, because you have a mathematical that keeps the logs all the runtime. And we compare these two together, and then that would allow us to do the saving, determine the saving. Now, if somebody has, say, for example, programmable thermostat that they actually programming, that would allow them to save more because when they go away from the home, they set a lower set points, the temperature they're saving less compared to that baseline. But it varies by the house. And maximum, we've seen savings of up to 23-25%. But on average, the average house, the numbers were small, around maybe 15%. There's different methodologies also confirm that it's 15% or so for average home makes sense. But some homes actually don't save anything because they are very much acclimatized. So the houses, the people who are, wear sweater in winter at their home and like can open up the windows in summer or whatnot, they actually save maybe nothing.
Okay, great. So to our audience, continue to send questions our way through the chat box. Here's the next question. How do you think the role of Apache Spark can be in this system for more faster response?
So maybe I can start, and then Sina, feel free to jump in as well. From Vertica's perspective, I mentioned during my presentation Vertica's commitment to open source integration. Apache Spark is one of those tools that Vertica integrates with. So we have bidirectional integration with Apache Spark, so you can move data from Spark to Vertica, and then Vertica back to Spark. Most of the customers that we see, they're using Vertica alongside Spark. They're using Spark more for real-time transformation of data, and then they're moving data into Vertica to be housed for longer periods of time and to run more complex, deeper, faster analytics. We do have some benchmarks that we've actually done with Spark using our ML functions where as you scale the volume of data, it's much more performant using Vertica to run those machine learning functions than using Spark. But certainly there's instances where you can use both or either. And Sina, please feel free to jump in as well.
So I think I'm not sure the question is, if the question is how do we fit Apache Spark into this in the system, like there's no way you could combine Apache Spark with the Vertica. It's like there's two different things. So Apache Spark would be for the time where I showed you like if you look at a chart, remember that there's this kind of analytic layer on top, there's a database layer, and then there's data in the between. In the middle, there was the ETL process. So that ETL process right now we're running it on, say for example, Python script on a machine, independent machine. That's where you can run Apache Spark. So you have a Spark cluster in which loads the data, manipulates data, for example, for ETL process. That's what usually people do with Spark. Or if you want to do processes, so data sits in the database, you pull that data from a database, for example, Vertica, and then you have another data come from somewhere else, then you manipulate them into Apache Spark. So what Spark provides that computational cluster to do the computation. So in a way, it's sitting beside some sort of after or before database, depending on where your data comes in. So data comes to the Apache Spark, Spark sends it to the database, or data comes in from the database, sends to the Apache Spark. Faster response from the database, that would not be able to improve the response of their Vertica using Spark. But maybe the entire pipeline, for example, from the beginning when you have the data coming in, if you run it by Spark, maybe, yes, it's faster than if you do ETL, maybe individually on a single node machine, because Apache Spark can parallelize that and we can speed up things.
Great. So some Vertica specific questions. How did you scale out the Vertica cluster? Did you start with a single node and add it as your demand increased, or did you start with a 3-node cluster?
So we did start with a 3-node right away because we knew that our computation is like we knew the details of what we want to do. So we set up a 3-node cluster and we are fine still with it. The good thing is that we had it on AWS. So if you had it on the cloud, we can change the machines if we want to change it. So we started with the big machines, with the big like this 2x, like basically C4 4x large type instances, very large machine with like 32 CPUs each. And then we realized we don't need that much expensive machine, so we reduced it down the road to smaller machines. So we changed the instance type, the machines itself, but we always kept that the 3 nodes. And we found it's going to be easy because you can either change the machine, but I don't know if David, you want to explain more on the actual expansion of the nodes?
I think the note is just on scaling out the Vertica cluster. I mean, the question was on that. There was a follow-up question on do you use it for the Spark? Does the Spark node run on the Vertica nodes? And
I didn't run Spark on Vertica node.
Okay.
Yeah, typically Spark would be run alongside Vertica, not on the same nodes, and you'd be moving data from Spark into Vertica, typically for what we see for longer-term data storage and analytics.
Great.
And generally speaking, in terms of Vertica, most of our customers oftentimes do start out with 3 clusters and then scale up depending on their volume growth. So Vertica, because it's massively parallel processing and can scale out, you just add more nodes to handle larger volumes of data as you grow.
Great. So continuing on the Vertica questions, are Vertica's in-database machine learning functions a separate package or library you will have to install, and what is the additional pricing?
Good question. So all of the machine learning functions that I spoke about on the webinar today, all of those come out of the box with Vertica. So there's no need to download or install separate packages or pay for additional features. All the machine learning functions I mentioned do come out of the box with Vertica. And if you want to talk more about that off the call and in terms of pricing, we can certainly discuss that.
Okay. So in addition, this is another question here. So we got a great use case here for Ecobee. In addition to the smart thermostat data with Ecobee, what are some other Vertica IoT use cases or customers?
Yep, so I can answer that again. We have a number of customers using Vertica for IoT use cases, and they really run the gamut. I mentioned a few earlier on my logo slide, including Optimal Plus. They analyze manufacturing and production data to identify product defects and perform root cause analysis. We have a customer, Anritsu, which is a communications and electronics equipment manufacturer. They use Vertica to support their telecommunication customers to identify network capacity issues and constraints. Sunto is another customer of ours. They're in the wearable space. They sell very high-end sports watches, and they use Vertica to analyze the data coming off of all of their customer exercise regimens. So those are just a few examples, but they really do everything from manufacturing to wearables to telecommunications. We have a number of customers using Vertica for IoT use cases.
Okay, great. Thank you. So we have a few more minutes here, a few more questions. If anybody in the audience has some questions, please send them our way. We will try to get through them. Going back to some technical questions here, what did you do to migrate the data from larger machines to smaller machines? AWS, DMS. I'm not sure what DMS is, but maybe you know.
Yes. So we used, so our data, maybe it was around 10 terabytes. It wasn't huge by the means of data, big data these days. So we used nothing. We just really pulled basically like you have the MySQL command through the TCP/IP like connections. Typically, we use the S3. We just use the S3 commands through the simple networks, and that was sufficient for us. But if you have a larger data set, I've heard of the AWS tools as such, but I haven't had the experience personally.
Okay, great. Let's see here. Next technical question. Was the application example used for demand response events an application that is available through Vertica or an added feature? And I think, this was for a section in your presentation, if you recall.
Yes. Yes. So these functionality, just example I showed you today, none of these were like features of Vertica. So these are basically there's a plethora of the machine learning tools around them to calculate temperature properties of the house, to run optimizations, to basically respond to different things. I believe the one that so those are separate scripts. So we basically use Vertica as a data source to run data, to pull data, to run certain analytical functions inside. Now, I think maybe your question is around the Tableau, like the visualizations that you saw from the graphing tools. Those also done. That's the visualizations done in Tableau. So there's a good relationship between Tableau and Vertica. So you can put a query, a SQL query on the Vertica using Tableau, and you can visualize data in Tableau. So the data was in Tableau. The data is in Vertica. We pull the data, we organize them, run some sort of SQL command, stores that data to another table, and then put Tableau on top of this. So you can do your query. So what you see really is a very agnostic way. So it could be any database. It just happens to be the Vertica sitting there, and then Tableau queries it.
Okay. So keeping that theme in mind, here's a separate question. I'm back to Spark. How does the data travel from Spark to Vertica?
Good question. So Vertica we have a bidirectional connector with the latest release of Apache Spark. So using that Vertica connector for Apache Spark, you can save data from the Spark data frame to Vertica tables using the data source API. So it's a bidirectional connector.
Okay, great. Back to a Vertica question, and I think we're getting near the end here. Are free trials available for Vertica, and what are our options for trying it before purchasing?
So the answer to that is yes. If you go to www.vertica.com/try, there's a few different options. We have a few test drives available on AWS and Azure where you can get started with data and play around with Vertica very quickly. We also have what we call Community Edition that you can download. It's a up to 1 terabyte, 3-node installation of Vertica. There's no time limit on it. There's just a 1 terabyte max. So you can download that, no questions asked. But if you go to vertica.com/try, you'll have all the different options for getting started on Vertica.
Okay. I'm going to let one last question in. If you guys can keep this short, we'll wrap it up at the top of the hour. It is about Kafka streams. Have you explored Kafka streams and to create a direct link into Vertica?
No, we're exploring Kafka, but that Kafka, maybe David, you can explain if Vertica has a Kafka link.
So yeah, I can answer that. We do have connector with Kafka, so you can use the Kafka messaging bus and use Vertica as the landing database for data that's streaming through that Kafka bus. I don't know, Sina, if you've used that functionality or not.
No, we don't use it, but this is something we're considering.
Great. Well, thank you. Great answers to some very good questions. For those of you that asked questions that weren't answered, we will be sending all unanswered questions to our panelists and the Vertica team so that they can follow up with you after today's webinar. I just have a few quick announcements. Please mark your calendars for October 31st and our next IoT Central webinar sponsored by Eris. Also, this taping will be available for on-demand viewing later today and can be found on the homepage of IoT Central at iotcentral.io. This brings today's webinar to a close. I'd like to thank our audience for their attendance and thoughtful questions, and a special thanks to Vertica for their sponsorship, as well as to our speakers, Tina Shahandi and Benjamin Smith, for their insight in today's topic. My name is David Oro. I'm very pleased to have been your host. I look forward to seeing you all again on October 31st. Have a great day.